Hello guys, welcome back to my channel Code Craxes. Today we are solving a very important question from the Must Do Question series of Google. This is named Jumping Numbers. It is important because it is based on graphs, and if you're sitting for any interview of coding in DSA is included, then you should know graphs, especially the DFS, BFS, Dijkstra algorithms. These are very important, and hence this question becomes one of the most important question for our series. Also, this is a question which can be asked directly, like it is already so much complicated, they can also mix CP with it, but it's a very unique and tough question in itself, and hence it can be asked just directly as it is. Okay, so now let's read the problem statement. It states that given a positive number x, find the largest jumping number which is smaller than or equal to x. And we are defined with the jumping numbers definition, that is, a number is called jumping number if all adjacent digits in it differ only by 1. Because that means 8987 is a jumping number because 8 minus 9 is 1, 9 minus 8 is again 1, and 8 minus 7 is also 1. But this is not because 9 minus 0 is not 1. Okay, so now let's try to think about it. So a simple solution of this question is also important. So if you see, suppose 345. 345 is our jumping number because all the digits are like this in it. So what we can do, we can simply run a loop from I equal to 1 to x and search if a number is a jumping number, and if it is, then we can return it, or we will iterate backward so that at least we can save that much number of like suppose 345 is itself a jumping number, so we will start iterating from I equal to 345, and we will have a function to check jumping numbers, and it will return true in case of 345, and hence we are good to go, like we are done with this code. But however, if you carefully analyze the time complexity of it, if you trade like this, then it can save, but again we should keep it like this only because maybe it's a possibility that we are given x equal to 1, then also like you understand the time complexity will remain in this case O of x, that is the we have to iterate from 1 to the number, so the iterations are like this, and the problem will become O of x time complexity. But if you see carefully in the question, it is given that x can be up to 10 power 9, and hence because of this constraint our we will get a time limit exceeded error in this case. So this is a potential starting solution. It is a simple solution, but now we have to think for the efficient one, right? So if you carefully observe, suppose we are given an element 6, 7, 5. Okay, it is not a jumping number. So what we can do, we can search for all jumping numbers the way we are doing before. For all number before 675, right? One of them which is the closest to m will be our answer, but there is a difference. Here we are running a loop from 1 to x, where maybe we will also be hitting 13, which is not a jumping number. We will also be hitting 15, which is again not a jumping number. So the crux is just iterating over jumping numbers, right? Like solving it for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are all jumping numbers. Then we will go to 12 directly. Then we will go to 21 directly. Then we will go to whatever, like 23 directly, then 32 directly, whatever are the jumping numbers. This will efficiently decrease our time complexity to O of, suppose k, where k is the number of jumping numbers till our x, whatever our x in 675. Before 675, how many jumping numbers are there that are k, and so our time complexity is reduced from ox to ok. So this is the crux, that instead of iterating from I equal to 1 to x, we will just iterate over the jumping numbers. But now we should have something, some data structure or something array to keep all our jumping numbers in account, and so that we can reach to the answer. So here comes the approach of BFS. Why BFS? Because before BFS, let's think how can we make jumping numbers. Suppose we are given 1, then 1 plus 1 will be 2, and 1 minus 1 will be 0, and hence we can make two jumping numbers from 1. Let us take 12, which is again a jumping number. If I do 12 into 10, I'm just trying, 12 into 10 plus 1, it will give me 120 plus 1, which is equal to 121. It's again a jumping number. Similarly, I will do 12 into 10 minus 1. See what it will give me. 120 minus 1, which is equal to 120 minus 1 is simply 119. Yeah. So this is not a jumping number. So I think that this method is wrong. We cannot generate by multiplying it by 10. What if I keep the track of just the last digit in mind? So it will become 20 and it will become 21. Yeah. Again 12 to 10, then 20, then 90. I think this is also not happening. So we have to search of what can become a potential answer in our case. Okay, let's think about it. Okay, so let's try some more things. Let me do 12 into 10. Then I can add the last digit. And then I can add 1 in it. What it will give me? 120 plus 3, I guess. That is 123. Then 12. 12 into 10 plus 2, the last digit, minus 1. What it gives me? It gives me 120 and plus 2, that is 122, minus 1, that is 121. Yes, it is giving me a solution. So we can generate jumping numbers by doing number n into 10 plus the last digit of the number plus or minus 1, right? So this is the crux. But let's see what happens if we have some element like 89 where 9 is coming at last. So let us try it. 89 into 10 plus the last digit 9 plus 1. What it gives us? 890 plus 9 plus 1. That is surely, I think, 99 plus 9, 900. But it is not a jumping number. Then let's check for another case. Plus 9 and minus 1. So this is giving me 899 minus 1. That is our jumping number, 898. So in case of 9, only minus 1 will hold true, right? It will give me a jumping number. And similarly, let's try for the case of maybe 10. Yeah, we have to handle 0 also, because in this case what will happen? Let's see, 10 plus 0 is the last digit. Since 0 is the last digit, it can cause us problem. 10 plus 1, this is 101, holding true, good. Then also try for the other case, that will be 100 minus 1, right? And that will be 99, not holding true. Oh, sad. It's not holding true. And hence we got our last case, that in case of 0, what we have to do? Only plus 1 holds true. That's it. So I think that we developed something about the jumping numbers, that this is the code to make jumping numbers. And what we can now do, we can simply run a BFS to generate all these numbers. And if we get a number that is smaller than or equal to x, we will update answer. If we get a number that is smaller or equal to x, will update our answer, right? KR. Sorry for the errors. Oops. Yeah. Let's I think that the crux is clear. We have to make the jumping numbers and we will iterate and check only in the jumping numbers that if we are made at it. So we will start making the jumping numbers from 1 to 9. I think this will cover all our jumping numbers. Let's try to do this. Okay, first of all, I will start iterating for long I equal to 1. This will start my code I less than equal to 9 and I less than equal to x also, because this might be enough. Checking till x, maybe x is 3, so we do not need to go beyond it. Okay, I think with 9 only, 9 is the last element, because till that we can achieve all our elements. 9 will go further to, let's check, 9 will go further to 90 plus 9 plus 1, and that will yield me not plus 1, minus 1, because it's 9. So 98, right? And then 98 will again go, then 98 might make 989, then it will again proceed. So in this way we will make all numbers from just 1 to 9 iteration of the loop. All the jumping numbers can be made. Okay, then we will write a BFS function which will generate the numbers for us, and we will check for I, X, and let's call it answer. Let me declare an answer here. Int answer equal to initially 0. Okay, then let me write the code void BFS. It will have long I, long X, and long ampersand answer, because we will change its value, manipulate its value here. Okay, then let me take a Q of long, that will be Q. We will push our num. Let me name it num. It sounds good, right? So we will push num in it, because initially starting point is always num, right? Starting point is 1 here. Okay, then after pushing it, let me write a loop for while Q is not empty, right? We have to check for the out of bounds condition. Then my num, I will make Q dot front the first element, and then I'll pop the element because I need to generate it. Then we will check if num is less than or equal to x. This is important. If it's not, then we will go out of the loop, right? Like we will break the loop. Okay, so if it is, then first of all let me update the answer. My answer will be max of answer minus num, not num. And then what I will do, I will check the last digit, right? We can take this as int only, and last digit equal to num modulo of 10. It gives us the last digit. Then what we can check, if the LD is not equal to 9. What we check for 9, let us see. The 9 condition holds true only with plus 1, right? Yep. So we will just do plus 1. Am I right or wrong? Let me check it carefully. Oh, sorry, I have tried for the 0. That's why I'm checking. Only for minus 1 it's holding true. Okay. So if LD is 9, is not equal to 9, then what we can do? We can do num equal to, what we can do? Yeah, simply num into 10 plus LD minus 1, right? And if LD not equal to, and this we can push, right? Q dot push num, and not num. Yeah, and if it's not equal to 0, then we can push Q num equal to num into 10 plus LD plus 1, and we can push num, right? Else nothing will be there, and I think we are good to go. We will return answer, and let me declare it as long so that it does not give error. I think that our code is problematic. I think that maybe I have pushed or pulled it wrong. Let me see. X was not declared. Yeah, obviously it was not declared because it's a small lettered word. I hope my code is working fine. Yeah, it's working fine. Strange, I thought that it might be errors. Let me check. Yeah, there are errors, exactly. Our code output is 65 for input 69 with the correct answer is 67. So 65 is my output. Maybe the error is this. Let's try to fix it. Okay, so what have we done? Yeah, so I think that this is the error, right? We do not can't change num here. It is already a value. We can directly push into the num. It will manipulate num 2 times, and then it might be problematic for us. Let's see now. I think it should work because we have to just push the element right in it. Uh, Evaluating. Yeah, it's working for this. Let's try for the case it's not working. 69. Custom input we have given to it. Expected output. Yeah, it's working fine. Let's try to submit it. Still we have got error. Your code output is this. So guys, you're seeing we also have to like think about what error we are causing and try to like fix it also in this problem. So let's think again of what problems we are getting. So, okay guys, it took me a lot of time to figure out what my error was. Let me tell you this, that here we are checking if the last digit is not 9, right? So, if it's not 9 means it's 0 or any other number. So, there we have to write the condition for 0, and here we write the condition of -1 for 9, and I think now it should work. This was a little mistake, but it's take a lot of time to figure it out. Let's try to submit it. Yeah, it got submitted finally. And so we have to take care of these conditions, right? This means that if LD is not equal to 0, then that means we have to keep track of the condition from 1 to 9. So here the ninth condition will play, and here for the 0th. Here we are just updating our answer, and this is the code for the BFS. And I think that's it for this video. We are good to go with this code and all. I hope you got the crux of this question, that is to just iterate over the jumping numbers and formulating it with the help of Bradford search. Also, I will try to make a separate video for BFS and DFS because they are very important. They are used in a lot of questions, and until you don't know basic BFS and DFS, it will be problematic. Okay, so bye bye for now, guys. Thank you for watching. Bye.